Hello viewers, welcome back to the channel ThinkScalable. Today we are going to solve the LeetCode Weekly Contest 482 and we will try to solve all the four problems of the contest and let's see how we go. So without getting further delays, let's move on to the first problem. So the first problem says maximum score of a plate. You are given an array nums of length n, choose an index I such that I is from 0 to n minus 1, and for the split operation at any index I, the score is calculated how? Score is calculated as prefix sum of I minus suffix min of I. Okay, then return an integer denoting maximum score over all the valid split indices. Okay, great. So let's start with this example and let's move on to the notepad. Let's take this example, first one, right? Split index. Fine. And the array given to us is 10 minus 1, 10 minus 1. Then we have 3. Okay, makes sense. Then minus 4 and minus 5. Right. And answer for this is 17. How we will see? This is the nums array. Fine. Now, if I try to further simplify the question, it is basically saying we have to maximize the variable score, and how they are defining the score is score of I is nothing but you can see prefix sum of I, prefix sum of I minus suffix min of I, suffix min of I. Fine. And I hope you all of you must be aware of prefix sums, right? Prefix sum is you are going from left to right. So prefix sum up to this index is 10, from there up to this it is 9, then 12 and so on. Prefix means you are going from left to right, suffix is you are going from end to forward direction. It is from right to left. Okay. So this is a very easy question based on pre-computations. We will iterate over all the approach. What will be the approach? Iterate over all the indices, and if you are on a particular index I, you will have already pre-computed the prefix sum up to this index and also the suffix min up to this index. You will simply use this formula and get what is the score corresponding to this current index I. That is, if we make a split over the index I, what will be the score? And you will also maintain a global variable answer and keep on updating this variable, right? Okay. So if you want, I can do a dry run. For this, the prefix sum, I'm using PS variable for the prefix sum. Right. So prefix sum will look something like 10, then 9, then 12. This is what 8 and 5. Right. 10, then 9, then 12. Okay, 8 and just a second. This should be 3. This is 3. Fine. And you have to find a suffix min, suffix min. Initialize this. This is the minus 1, and up to this, what is the minimum? Minimum of this thing and the current one, which is minus 5, and again up to this suffix min is gonna be this. So while computing, let's say we are having a variable answer, right? Answer initialized with infinity max, and at this index, what will be The score is nothing prefix sum up to this index, which is 10, 10 minus the suffix min, giving you 15. So answer this will be updated with 15. Now moving ahead, at this index prefix sum is 9 and the score is 5, giving you 14, which is lesser than the answer, so we will not update this. Here we will be having 12 minus 5, which is 17, better than the previous answer, updated, and so on. So that's why the answer for this test case is 17. So let's now move on to the coding part. Fine. Then we will be discussing the time and space complexities. Okay. Now let's move on to the coding part. Coding part for this first, right? And I'm using Java as of now, and you guys can let me know whether you want to continue with C++ or Java. So as of now, I'm using Java only. Let's make the variable name a bit. I will not be focusing on the variable name here because I am having time constraint over here. So what we will do is we will first find the length of this nums array, right? Okay. Then we will declare the prefix sum array ps. Okay. Similarly, we will be finding the suffix min long sm means suffix min, right? New long. Great. Initialized with ps of 0 with a v0 means the prefix sum up to the 0th index is the element itself. Similarly, suffix min up to index n minus 1 will be v of n minus 1. These are the initialization. Then let's populate the prefix sum array starting with index 1, I less than n I plus. And how we'll be updating prefix sum of I is nothing but simply prefix sum of I minus 1 plus v of I. Similarly, we will be populating the suffix min. This was the prefix array. Now we will be populating the suffix array starting with n minus 2, I greater than equals to 0, I minus, and then suffix min of any index I. How will we be determining that is s min of I plus 1. We will be comparing basically math dot min. Compare this thing with v of I. Make sense? Once we have done the pre-computations, our pre-computation is ready. Now we are in a position to populate the final answer. So let's have a variable by the name answer, and we will be initializing it with a very smaller value, say long main value. Make sense? Now iterate over all the partition index or split index, starting with 0, going up to n. Fine. Now at each step, answer will be updated if possible. So we are using math.min, answer we found till now, plus the current score. So how we can find the current score? It's very simple. Current score of I is nothing but prefix sum of I minus suffix min of I plus 1. Fine. Once we come out of this loop, our answer is ready. We just need to return the answer variable. Let's compile it. Runtime error. Why is that? Okay, my bad. Now again runtime. This time what they are saying is runtime serializing long out of range. Okay, what could be the scenario over here is okay. Mhm. Okay, let's try to debug. N is ready. Prefixum is there. Suffix min, initialized prefixum, this thing. Populated a prefixum vector. Okay, updated suffix min also. Great. Then initialized answer with a very small value. Then iterating over all the indices. Mm-hmm. Each time doing prefix sum of I minus suffix min of I plus 1. Okay. Why it is given one time error? Okay, okay, got it. We are supposed to do max. My bad. Yeah, it does work. Let's try to submit it. Okay. Now, sorry for doing silly mistakes. Now, discuss final part is the discussion of the time complexity. It's very simple since we are using three loops, so order of n for each. So time complexity is order of 3n, which is equivalent to order of n. So linear complexity is there in this question. I hope you have understood this question. So let's move on to the second part, second question rather, right? Okay. Now the second question is minimum cost to acquire required items, right? This was the second problem. Now this was we can say not that much on the medium level. It was on the easier side, but it becomes kind of hard if we are not making some observations. What observations I will let you know. So let's go through the problem statement first. Minimum cost to acquire required items. We will be given five integers, cost 1, cost 2, cost both, need 1 and need 2. And three times of available will be there, T1, T2 and T3. T1 costs 1 and contribute to 1 unit. Similarly, T2 cost 2 and contribute 1 unit. But for the type 3, cost is cost both, but it has a special feature of contributing to both type 1 and type 2. And we have to collect enough items so that we meet at least need 1 and need 2. Okay. Return an integer representing minimum possible total cost to achieve these requirements. We have to minimize the total cost. Okay. So let's move on to the whiteboard and let's proceed with the blue color, right? So what does the second problem is saying is second problem question 2 is minimum cost to acquire required items. Fine. Minimum cost to acquire all items. And we let's pick up the first test case only. Cost 1, 3, 2, 1, 3, 2. Okay. First example itself. Cost 1 is 3. Cost 2 is 2. And common cost both is how much? It is 3. Makes sense. Then need one is need one is 3 and need 2 is 2, right? Need 2 is 2. Great. And in this case, the answer given to us is 3. Let's see how the answer is 3. So we need to make some observation, right? So if we rewrite whatever has been mentioned in the question, we are given 3 types of items, like T1 type of item, T2 type of item, and T3 type of items. This contributes 1, T2 contributes 1, T3 contributes 1 unit, and this costs C1. Let's call it as C1. This costs C2, and this contributes 1 to T1 plus 1 for T2, and costs what? Let's call it as a common cost CB, right? Common cost CB, C1, C2, and CV. Now, tell me one thing, one observation that we need to make is, in order to have 1 unit of T1 and 1 unit of T2, we have two choices. We have choices. Either pay C1 cost and C2 cost, or we can pay common both cost, CB cost, right? So which one we will be picking depends on which out of these are minimum one, because one T3 item can satisfy T1 need and T2 need one each. And if you are not going by that part, then we have to take those elements separately, paying C1 and C2. So there can be scenario that three cases can be there rather, right? Let's try to draw this. First, this is need one item N1, need two. This is case 1. Then case 2 could be N1 is bigger and N2 is smaller. Case 3 can be what? N1 is smaller and N3 is smaller. Fine. So in this case, how will you compute the answer? In this case, answer will be simply the minimum of C1 plus C2 CV. It means either in order to satisfy one T1 need and one T2 need, pay C1 cost plus C2 cost, or simply use type 3 item and pay CV cost. In this case also, let me change the pen color. So you can notice that this much part is common in this. Similarly here also this much part is common, right? So based on that observation, what we can say is these two scenarios boils down to case 1 only. So case 1 answer plus some extra. Here also we will be having case 1 answer plus some extra. And what is this extra is, and this extra is nothing but this is the extra part. So how will you determine the extra part? This is N1 minus N2. This is the extra part. Now in order to satisfy this extra part, we have two choices: either pay C1 cost or go with CV. Similarly here the extra part is N2 minus N1, and again in order to satisfy this we have two choices: either pay C2 cost or satisfy it with CB, because it is mentioned in the question that there should be at least these many items and need 1 and need 2. There can be greater than out also. That's why they are using the terminology at least, not exact. Fine. So we will code up this all the three cases. So if we combine all the three cases, what we can do is we will first calculate the base answer, which is this. This is your base answer. So total ans final answer is nothing but your base answer coming from case 1 plus depending on whichever case is there, we will have some extra, right? So if you pick up uh, this example itself, in this case, if I try to draw it, need one is, this is the need one and this is the need two. Fine. So we will compute the base answer. How? Base answer will be this much part, common part, that will be minimum of C1 plus C2 or common. Why? Because in order to satisfy these common part, which is 2, we will either use 1 unit uh, of T1 and 1 unit from T2, or we can use a single type 3 operation and get it. So whatever is minimum, we will pick this. So in this case, minimum of C1 plus C2, which is giving you 5, and CV common cost is, how many units are there? For 2 into 2. So minimum of C1 plus C2 is 5 comma 1 into 2. 2 into 1 giving you 3. And one more thing, have I taken this example correctly? 3 2 1 3 2. Make sense? Okay. Fine. Just a mistake. 2 into 1 is not 3, it is 2 itself. That's what I'm thinking. Why, where I am doing the mistake. Okay, let's continue. So it is 2. Now we have to need to calculate the extra answer. How will you find the extra answer? Extra answer is this remaining part, which is 1 into minimum of cost 1 and common cost, which is what? Minimum of 3 comma 2, min of 3 comma 1 rather, giving you 1 into 1, which is, so final answer is base and extra is 1, giving you. I hope you have understood it. For the common part, we will be using the base formula, and in order to calculate the extra one, we will decide based on whether n1 is greater or n2 is greater, right? So let's move on to the coding part of the second solution, right? Okay, this is the second part, right? Let's start coding. Okay, so let's define a variable by the name resultant res, and we will keep on populating this res, right? So we will first compute the base answer. Base answer is what? Base answer is nothing but math dot min of uh, this thing, cost 1 plus cost 2, or this common cost, type 3 cost. Whichever value is smaller, I will multiply it to satisfy the need of what? The common part. How will you determine the common part? Let's say one pillar is of height 3 and one other one is of 2, so common part will be minimum out of those. So math dot min of need 1, need 2, whatever value is minimal, you will pick it that up, right? Now moving forward, we can encounter some overflows, integer overflows, right, based on the constraint. it can go to integer overflow, right? For example, the cost is 10 to power 6 and need is 10 to power 9. So it is 10 to power 15 and integer range is generally 10 to power 9. That's why we are using long. So in order to handle that flow, let's add a 1L, right? The base answer is ready. Now handle the remaining one. In order to handle that, what we can do is we will put a check which case is there. Whether it is case 2 or case 1. Which cases I am talking about? I am talking about these cases, right? These ones. Whether n1 is bigger or n2 is bigger. Fine. So if your need 1 is greater than need 2, then in that case your first pillar is bigger one. Tick. And then in that case, how will you find the remaining one or balance one? Need 1 minus need 2. Fine. And to the resultant, add the extra feature. Extra will be the remaining and the mean. What I will pick is math.mean of what? Cost 1 and common cost. Make sense? If you want to repeat, I can. The remaining part into again you have a choice whether to satisfy the remaining part with cost 1, that is using T1 items, or use T3, whichever is minimum you go there. Now you might be thinking, if you use T3 items it will contribute to other one also, then that is also fine, because it is mentioned there should be at least these many numbers. If there are some extra, then also it is fine, right? The second case, else if need 2 is greater than need 1, in that case how will you find the balance one? Remaining one will be need 2 minus need 1, and a resultant will be having remaining into whatever is minimum out of cost 2 and cost both. You just pick it there. And after that just return it, as simple as it can. Let's cross check again. Resultant variable base answer has been calculated based depending on whether the sum is minimum or common cost is minimum, then multiplied with the common count. How will you common count? One bar is of height 3 and the other bar of height 2. To find the common one, we will pick up the minimum one. Our base answer is ready. To that, we will be adding the extra part. How will you determine extra part? Find the remaining part, eliminating the common one, and multiply it with the cost. And in order to satisfy, again we have a choice whether to satisfy it using T1 operation or T3. If you are using T1, cost will be cost 1. If you are using T3, cost both will be used. Similarly this thing. Let's try to compile it. Yeah, it is working. Now let's try to submit. Okay, it does work. Discussing about the time and space complexity. Here we are just using the variable, accessing the variable. So constant time operations are there. So we can say the time complexity is um, near about constant only, because we are not using any for loop or anything else. We are just accessing the variables and using this math min functions, right? So this is having constant time and space. Now moving on to the third problem. We said smallest all ones multiple. You are given a positive integer k. Find the smallest integer and divisible by k consisting of all digit ones. So the number n has special property. So if I go to our notepad, it says this is third problem, right? Let's change the pen color. Let's zoom it a little bit. Fine. This is our Third problem Q3, which says smallest all ones smallest all ones. They are saying we have to find smallest integer n, smallest integer n such that n mod k equals to 0, right? N mod k equal to 0. Indirectly, n is divisible by k, and n is of these forms only, all ones, either 1 or 11 or 111 or like this. They will be having all ones. Now we have to find the smallest n. Now, as I was saying you, that third problem is based on some mathematical observation, right? So if you extrapolate this thing, n mod k, this can, using the modular arithmetic, we can write it like this also, right? Instead of 0, let's we want what? Okay, let me explain this thing in a much better way, although this will take some time, but that's okay. N mod k is equal to some remainder, right? Let's remainder is called as r. So if you do one thing, just a second, if you extrapolate, this can be written as this thing also. Why? Because if you simplify it, this will get cancelled out, right? 10 10 gets cancelled out and you are left with n mod k again. So this was the part. Why we are doing this, you will let you know. Because if you go by the brute way says, let's say initially your number was, you start with n, then you go to n 1 1, then this. So you can see how the numbers are rising. And if we go by the brute way, and you see the constraint give mentioned in the problem is tends to power 5, k can go to tens to power 5, right? So if we go by the this way, then there are chances that it may get overflow, right? So to efficiently handle this thing, instead of doing this thing, we will be dealing with remainder remainders instead of actual numbers, right? Rather than storing these bigger numbers, go with the remainder. That will do the same thing. How? I have proved it. Either you do n mod k or do this operation, both are equivalent, right? So we will just handle the remainder of. Fine. So let's take example k3 and k7. K is equals to 3, right? If you take this example, and initially let's say remainder is 1, and the number of times we have done this, what is this count variable? Count variable will represent the count of ones in number n, right? So initially let's say the remainder is 1, basically number n is 1 and it is having 1 as the number of ones. Fine. Okay. So moving forward, let's try to simulate for k is equals to 3. Right. And you will observe something interesting. What is that? So initially remainder is 1. Right. Then what will be the new remainder, because we are keep on updating the remainder, no? The old remainder is into 10 plus 1 mod k will give you the new remainder. Why? Because we have 1. How you go to 11? You will simply do previous number into 10 plus 1. How will you go to 111? Previous number, which is 11 into 10 plus 1. So remainders are also moving in a similar fashion. Previous remainder dot 10 plus 1 take modulo with k, right? This will give you the new remainder. Fine. So you will observe something new. So remainder getting updated to old remainder, which is 1 into 10 plus 1, 11 mod 3 is how much? 2. Now again moving forward, new remainder will be 2 into 10 plus 1 mod 3, which is 21 mod 3 equals to 0. So as soon as remainder becomes 0, because our goal was to make this remainder equal to 0, right? That's what we are doing. Since remainder becomes 0, it means indirectly n mod k become equal to 0, because this was equal to remainder only. So we will stop. How many operations we did? Count 1 time 2. So count becomes 2 here. Here count becomes 3. That's why the answer here is 3. Make sense? So we will put it in a while loop, that till remainder is not equals to 0, we will keep on doing these things. We will find a new remainder which is equivalent to old remainder into 10 plus 1 and take it modulo with k, right? Count will be initialized with 1, the remainder initialized with 1. Why? Because we have assumed that remainder initial number is equals to 1 and it is having number of ones as 1, right? Make sense? Okay, keep on updating this thing, and each time we do the operation we will do count plus plus and remainder will be updated. Just a second. Remainder will be updated. Update to what? Remainder will be updated with, just a second, let me clean up working arena. Fine. Now each time we are doing the operation we will increment count by 1, and then new remainder, the remainder will be updated with this updated remainder. We will keep on doing this for loop. Update remainder, increment the number of operations, means number of ones present in this number, and remainder will be updated with this. We will keep on doing this. When once you come out of this loop, the this thing count will represents the number of ones present in number n, the smallest one, which is our answer. But there is some interesting thing. There can be test cases like this. When k is equals to 2, k is equals to 2, you will again initialize remainder with 1 and count as 1 and again enter the loop. If you do the dry run of this, what you will do, initially remainder is this, then the updated remainder will be what? 10 into uh, 1 into 10 plus 1 mod 2, giving you how much? 11 mod 2 carry 1, the again new remainder. So did you observe something? What? You started with some remainder x, you again reached a step where remainder is x. It means you started from some location after some number of moments, you again reached it. It means there is a cycle. It means there is a cycle, or you are got stuck inside infinite loop. So it means if you are seeing any remainder, seeing any remainder x which is already visited, then you will say that there is no way to make it equal to 0, and we will simply return -1. It means it is not possible, right? So this was the edge case, that if you encounter any remainder which has been visited earlier, then in that case you will say it is not possible. Fine. So let's recap what we have done. We were supposed to find n mod k, which is equals to remainder, and we have to make it equals to 0. Since directly storing these bigger numbers was headache for us, so we used our modular arithmetic, and instead of dealing with numbers directly, we were tackling the remainders, and we kept a variable count representing number of ones in n, and the number n is being replaced by remainder, and we will keep on updating remainder each time, increment the count, and if we at any stage encounter the same remainder we have already visited, we will report that there is an infinite loop and there is no way to make the remainder equals to 0. So we will straightforward return -1 from there. So let's move on to the coding part of the third problem. So in that case, okay, in this we will keep a visited array kind of thing to keep track of the remainders we have seen so far. Fine. And since we are taking, why we are taking k plus 1, because remainder can have value up to k only. For safer side, we are taking one more extra, right? We will start our algorithm taking remainder 1 and in count equals to 1. It means this count represents number of ones in the number we want, right? So let's start the algorithm, which says keep on running this algorithm while remainder is not equals to 0. Fine. We will compute the new remainder. For that, it will be nothing but old whatever was there in the old remainder. We will multiply a 10 over there, add a 1, then take its modulus with increment the number of ones, because each time we are doing operation, it means we are increasing one number, count of ones by 1. So if at any instant you get to see that new remainder turns out to be equals to 0, then straightforwardly return count from it. And another edge case was if we have seen this new remainder already, then it was a cycle, return -1, not possible case. Fine. And update the visited with this new remainder, saying that we have visited this remainder. Fine. And the remainder will be updated with this remainder. Fine. So now once we come out of this loop, which will not be the scenario, So if I recap why we have taken the visited array to keep track of the remainders we are seeing so far, remainder basically is a replacement or a substitute for number, because handling number can, as the numbers can grow, right? So instead of that, we are taking the remainders only. That will suffice. Count represents the number of ones in the decimal representation of that number, and we are running the while loop till remainder is not equals to 0. Each time we are updating the remainder and incrementing count by 1, saying that at each step we are moving, incrementing by 1. If we found the remainder equals to 0, because our aim was to make this remainder 0, then we will return count. If at any instant if you find the remainder we have already seen, it means there is a loop or cycle kind of thing. Straightforward return -1. Otherwise update the visited array and the remainder. That's it. And what mistake I have done here? Oh, visited. What else? Okay, let's try to submit it. Fine. So discussing of the time complexity, this while loop in the worst case can go up to what? K times. So time complexity is order of k. Why k times? Because we are taking what? N mod k, and the remainder value can go up to what? In this range? 0 to k minus 1. In the worst case, it will run up to k times. Order time complexity is order of k, and the space complexity is also order of k, because we are using this visited array. Okay, fine. Now let's move on to the fourth problem, which is the final one. And it was the hardest problem of all the contest, as we can see from the tag itself. Now, there's a prerequisite for solving this question. You guys must be familiar with the digit DP concept, because this is a straightforward implementation of digit DP. Because if you have earlier solved some problems of digit DP, you must be knowing that when we are doing something with the digits of a number, then in order to do it in efficient manner, we use digit DP. There are many hints, like we are given a range low, high, and we are doing something with the digits. So these two are enough to point you to the DP pattern, digit DP, right? Let's read number of balanced integers in a range. So you will be given a range from low to high, and any number n which is within this low to high range is called balanced if it satisfies both the constraints. That is, the number must have at least two digits, and the sum of digits at even places must be equal to sum of digits at odd places, right? Two constraints. There must be at least two digits, and sum of digits at even equals to sum of digits at odd, right? Now I will not be going much detail into digit DB, because that will take a hell lot of time, but I will I'm assuming that you know digit DP, and you have solved some, at least some problems on that, right? So let's go forward with the last and the final problem, Q4. Mhm. Q4 based on digit DP, dynamic programming questions, and in this you will be given a range low to high, and for any particular number n which lies in this range, it must satisfy two constraints. First, it should have at least two digits, and the second constraint is sum at even position should be equals to sum of digits at odd positions, right? Fine. There's a standard template of digit data, right? Which we guys generally, for those who have solve DGDP problems, they must be knowing what I'm saying, that there's a standard template, right? And for any DGDP problem, we generally have a function, let's say f, and we talk about index I. What is index I? Let's say we are building an digit. This is a number. Let's say this is a number x. So this index I represents on which location we are there. Also, we maintain some variables. These are basically the representing our state. We also maintain a variable type and start date or not. Fine. These things are common. Now, from now onwards, if constraints are very high, how to what were the hints? Hints were, we are talking about a range. Constraints are high, like in this question, constraints given to us is 10 to the power 5. Fine. And we are doing or doing some operations on digits of the number. So in future, if you see something like this, now we are talking about something in the range, constraints are very high, and we are talking about something and some operation, some constraints. Instead of operation, we can say conditions. This I would say, let's call it as a conditions. We have some conditions on the digits. Straightforward, go to digit DP. For that, we have standard templates. We maintain type is for sure, index is for, and the rest of the state variables are dependent on the question. Like in this question, we have to maintain other things also. And what are those things? We have to maintain even sum, odd sum, and a variable parity. 1, 2, 3, 4, 5, 6. We have to maintain these 5 variables. This represents the index. Title will represent what I will discuss a bit later. But those who have already solved digit, they must be knowing these terms, right? Started variable, sum of digits are even places, odd places, parity will decide whether the current index is representing a odd position or it's a even position. It's an odd position or it's an even position. Parity represents this. Odd positions are represented by 0 and even by 1, let's say, right? So if we talk about, there is a standard template, right? Why I'm saying again standard and standard, because as you will solve 2 to 3 problems on this topic, you will yourself realize that there is nothing as such. We will just paste the template and keep on update the states, right? So what is tight over here? I was discussing that. Let's say we have a number 1, 5, 6, 2, right? And numbers can be anything. Like we are building some number, let's say this, or 0, 0, 0. Here we are starting with 2. Anything can be there. 0, 0, 6, or 1, 1, 6, 5, or 1, 4, 6, 6. Any numbers, we will keep on. They are not continuous. I'm saying these can be numbers, which is, let's say this is the high and low is 1. So we can build this. These numbers can be there. No? Now, I was saying, what is tight variable? Tight variable basically says the number we are checking, its prefix. If the prefix is exactly equal, let's say we are having a number 1, 5, 6. So this prefix is exactly equal to this. So in this case, our tight variable will be turned on. Means it is true. Why type variable is 2? It is indirectly saying that we have the number, current number that we are building. These numbers are being built, right? So the current number that we are building is having the same prefix as of the desired number. Now, standing at this, we will check that since the current prefix is same as of given number, here we will have to be tight. It means the upper limit will be up to either will be 0, 1 or 2. You can go up to 2 at max because we have digits from 0 to 9 now. You cannot have upper limit right here. Why? Because you are bound by a tight. Your prefix is this. Because let's say you are not bound by 2 tight, that ink can go up to 6, 7, 8 or 9, which is crossing this range now. So in order to keep track of that, we maintain the tight variable. If you are not able to understand, then I will suggest to go through some videos on digit DP. You will get to. So in a nutshell, tight represents whether the number we are building is having same prefix as the given number. If it is, then type variable will 2, otherwise not. So in this case, type, if let's say we are building this number and up to this the prefix is not, so the type variable will be false here, false. And here you can place anything, if 0, 1, 2, 3, 4 up till 9, you place anything, it will not be crossing this range. That's the fact. Okay, so here I will paste the standard template of digit DP, right? That's not a big deal. Let's analyze the time complexity. We are using 6 variables, and generally time complexity will be dependent on the 3 variables. Index. What is index? Index representing any position in the number, and numbers can go up to 10 to power 15. You means you will be having in the worst case 15 places. Make sense? You will be going up to 15 places. So for safer side, let's say it's a 16 place. So time complexity is dependent on how index variable into, then we have a flag by the name tight, that will be either true or false, and then third one is started or not, fourth one is even sum, fifth one is odd sum, sixth one is parity. These are the variables. Index can go up to 16. Why? Because I have explained here, tight will be boolean variable, so two values it can take either on or off. Started is also boolean variable. Again, I am iterating. If you are not familiar with digit dipina, it will very hard for you to understand, grasp properly what I'm saying. So once you go through any tutorial, you will get understanding what is tight, what is started. And even sum can go up to how much? We have 16 places, and digit in the worst case can go up to 9. So this is how much? 9 6 are 54, right? So near about that. 154. Let's say it's near about 150. Same here, 150. Parity represents whether it is odd position, even that is also cool. So near about this is what? Too much, I would say, right? So, and this is this much, I would say. What I'm trying to say is, do we really need to maintain two variables, even sum and odd sum? Do we really need? I think we do not. Why? So in order to, for because this will definitely more time consuming. So in order to optimize this, what we can do is, instead of this thing, we can maintain the state because we have to keep index for sure, right? Type variable is also necessary. Started variable is also necessary to know whether the number is started or not. But these can be clubbed into one variable. What is that? The difference. Because ultimately we have to check whether even sum is equal to odd sum or not. So indirectly we can check their differences, right? So instead of having two states, we can maintain one state by the name diff. Parity we have to keep. So now instead of having these two states, we are just clubbing into 150. So that's a nice optimization. So let's now walk through the code of the fourth problem. As mentioned in the discussion, that final answer will be what? Calling this function f or high and then subtracting from low minus 1 will give you the answer. Why is it so? Because this solve function or f function of n represents what? Answer from this range 1 to n. We want answer for low to high only, right? So f of high will represent answer from 1 to high, and f of low minus 1 will represent answer from 1 up till low minus 1. So on subtracting this, we will get the answer in the range low to high, right? Okay, now let's go to the implementation of this function f. What does this function doing is, first it is checking an edge case, like if n is less than 1, it means there is only one digit, and it is explicitly mentioned in the question that there must be at least two digits in the number. So in that case, if digits are less than 2, we will straightforward return 0 from there. Then we are converting the number into the string and storing it into a character array. Then populating, and we are maintaining some global variables size representing the number of digits in the number and the character array s. Fine. Then we are calling this helper method with these arguments, and this helper method is taking first one index I. Type variable is started, the difference, and the parity. Parity representing odd place or even place. If it is 0, it means a odd place, and if it is 1, it is an even place, right? So the very first base case will be, if we are on index I equals to size, we have exhausted all the digits of the number, then we need to make a check whether the number we have obtained is a valid one or not. For that purpose, we will check two things: whether started is equal to 1 or not. It means the number started yet or not, because there could be a situation that you have exhausted the number and you ended up with this. That's not a valid one. And another one is difference equals to 0. If difference is equals to 0, the second condition, that sum of digits at even places should be equals to sum of digits at odd places. These two conditions are checked. So in this case, we will return that yes, we have obtained one number in the given range. Otherwise, we will return 0 because it's an invalid one, right? Then we will come back to this caching part a bit later. Let's iterate through the remaining ones. Now we will initialize a variable result and populate the limit. And these are the standard things. Limit will be depending on whether type flag is on or not. If type is on, it means prefix is same. So current digit is the limit. Otherwise, 9 will be the limit. Then we will iterate over all the digits starting from 0 up till limit and update the new type. Then check some conditions. If number has not started yet and you have something like 000 and you again got digit equals to 0, then in that case you will say that you will move on to the next location, next index with this new type, and 0 represents what? Number had still not started, because the prefix was having 0 and you again got 0. So number has not started. If will remain as it is, parity remain as it is. If this is not the case, then you will check whether which is odd or even. If it is odd location, then again move to the next index with the new type, and this time number started is on, and we will add the difference d, and parity will be flipped. If parity is equals to 1, it means it is even case, then in that case we will subtract the digit. So you can toggle this also. In one case you will be adding the digit, in other case it will be subtracting. It's not hard and fast rule that in case of odd you will be adding, or in case of even you will be subtracting. You can reverse interchange them, right? And flip the parity bit. How are you flipping? Let's say now parity is 0. It means you are standing at odd location. Next time you will be at even. So that's why paritability is flipped, right? And then return the result. Now recursive solution is there. In order to memorize it, we are using a 5-dimensional DP array, right? And here we are initializing it with -1, and then checking whether this state has been computed or not. If this state has been computed, we will straightforward return it without any computing. Standard memoization, and before returning we cache the result. That's it. Now one more thing, there is one more thing to notice, that we are using diff can go negative also, and if you try to access an index with negative, it is violating, it will throw you runtime error, right? Okay, so in order to handle this situation where the indices, the values can be negative, indices can be negative, those are being handled using the concept of offsets. You add some positive value so that it never becomes negative, right? So we are doing this. Here offset can be 145. From where did I get this number? You do this. 15 digits can be places can be there, and each digit can become 9, in the worst case giving you 144. For buffer we are taking 1. From there I got 145. Now this diff can range in this 145 to plus 145. So taking a buffer of twice this size, right? So offset into 2. Got it? Initialize the DP vector. That's it. And talking about the time complexity, there was a correction that in the notepad I said that time complexity is this thing. Here is the part where I have mentioned the time complexity. Yeah, here it is. Right. So there was extra factor over here. Extra 10 by for the inner loop. Right. That's why it index tight started even sum odd sum parity into 10. This is giving TLE. You can see easily. Now after clubbing these two into difference, the time complexity is simply index into tight into started into diff into parity into 10. So parity can be 2. This is 10 factor. Difference can go up to 145. Started 2, tight value with 2. This will be 16. Now this is within our constraint, right?
We'll go through the wastelands, through the highways, till my shadow turns to sun rays. And on we'll go through the wastelands, through the highways, and